Eric Burgess here, and today we're going to be doing some hypothesis testing. We have the following problem. The average person spends 5.1 hours a day watching television. A recent sample of 38 people revealed that they spend an average of 4.2 hours a day watching television. The population standard deviation is 1.8 hours. Using a 0.1 level of significance, can it be concluded that the average American spends less than 5.1 hours a day watching television? So we're going to be doing this using the p-value method. We'll also do it using the test statistic, and we'll be doing it using also the calculator in the chart. So if your class uses either one of those, you should be covered. So let's go ahead and just dive right in. Now, a lot of classes start with identifying the null and alternative hypothesis. I'm going to start by first pulling all the numbers out of the problem, right? Let's just get all the numbers out, and then we'll identify, what we need to do from there. So the average person spends 5.1 hours a day watching television. We've got the number 5.1, and we're told that this applies to the average person. So we know it's an average, but we don't know if it's a population average or a sample average. And so looking at the statement, it says the average person. So it's not tied to a specific number of people from some sample. They're just stating this about everyone. The average person spends. They're just talking about everyone. So this 5.1 is a population average. So we are going to write that mu, the population average, is 5.1. Okay, so that's our first number. And then it says a recent sample. We know samples are n, a sample of 38 people. And so we know, okay, well, n is 38. So we write that down. N is equal to 38. Revealed that they spend an average of 4.2 hours a day. So this average is also an average of watching the television. So this is just like our mean average, which is hours watching the television. And this average is tied to the 38 people in our recent sample. So this is going to be a sample average. So that's going to be X bar, and that's 4.2. And so if we look at this, if they're saying this is true about everyone, but look at this. When we did our study, we were nearly an entire hour lower than them. And look at this. Our population standard deviation, it says the population standard deviation is 1.8 hours. So sigma is equal to 1.8. We know it's a sigma because it's a population standard deviation. So check this out. Our standard deviation, the most people vary by, is around 1.8 hours, nearly 2 hours. We're practically half a standard deviation away from what this is, right? Because we're nearly 1 hour off, and approximately 2 is how much we vary. So this is very likely too high. Like, it just seems way too high, this 5.1. Doesn't seem right. And so we just get this just from looking at the numbers and sort of thinking about it a bit. We say, well, this is pretty high. So we've got our population standard deviation. Using a 0.1 level of significance, so our alpha is equal to 0.1, can it be concluded? Okay, so this can it be concluded thing is the alternative hypothesis. And in this case, it's what they want to conclude, so it's also the claim. So can it be concluded that the average American spends less than 5.1 hours a day? So the key word here is spends less. So let's go ahead and write out our null and our alternative hypothesis. So our null hypothesis, H naught, that's always that mu is equal to something. And so here they stated right at the beginning, mu is 5.1. So that's going to be our null hypothesis. Our alternative hypothesis, H1 or HA, is going to be that what they wanted to say up here. Can it be concluded that the average American spends less than 5.1 hours? So they're saying this mu, it's actually too big. It should be less than 5.1. That's what they're saying. And they want to conclude this. They want to say, can it be concluded? That makes this also the claim. So it's really, really important to realize, even though you've written down your two hypotheses here, you don't know what the claim is yet. You have to identify which one's the claim. Either one could be the claim. They could have said, can it be concluded that the average is 5.1? If they said that, then this top one would be the claim. But they didn't say that this time. They asked if it could be concluded if it was less than. So this also is our claim. Now, looking at our alternative, it tells us how many tails and which tail will be used. And looking at this, we see it's a greater than. And so we know that this is a one tail test, one tail, and it's a less than. So less than goes this way. So it's a left tail test. If it was greater than, it would be going this way, right? Because that's the direction numbers get bigger. And so we have got this. Now, if it was a two tail, it would have a not equals to, and that would be left and right. So that's the different combinations. So, all right, we figured all this out. We still need to know, are we dealing with a t test, a z test? What are we dealing with? And to figure that out, we look right here at our standard deviation, and we notice that it's a population standard deviation. Population standard deviations, we use a z test for. So cool. Now what we need to do is we need to draw our curve. We need to find our critical value, and we need to find our test statistic. Or if you're using the p-value method, you'll need to find your p-value as well. So we're just going to do all of that stuff. So first off, let's go ahead and draw our curve. I think having a picture helps a ton. It should definitely be something you do. Some students skip it, and then I see them get it wrong sometimes. So we know this is a symmetric curve because it's a standard normal distribution, right? Because we're doing z tests. So the middle will be 0. And we know it's a left-tailed test, and it has an alpha of 0.1. It's actually pretty big for an alpha. So we're going to have an alpha of 0.1, and it's covering the less than side. So it's going off to the negative numbers, right? Because this, I put 0.1 in sort of a bad spot. 0.1 is the area beneath the curve. But these values here, right, we have like -1, -2, -3, going off to minus infinity that way. So, okay, here's our 0.1 area. It actually could probably be bigger based on how I've drawn it here. And we need to find the value that corresponds to this, because if the value that we get for our test stat is bigger than this value, then it's pretty close to the population, to H naught, and it would land in here in this safe unshaded area. So we'd say, oh, we don't reject the null hypothesis. We think that this is right. But if the value we get is for our test stat is less than the critical value, if it's in the shaded region, then we would say, oh, we definitely reject the null hypothesis. And it seems like that's not right. So let's go ahead and let's find this critical value. So we know that it corresponds to an area of 0.01. And so we could use the chart or the calculator. Let's do the calculator first, and then we'll look it up in the chart. So this is a normal distribution, and we want to use an area to get a z-score. And so to do that, we need to do an inverse, right? Because normally we use z-scores to find areas, but we're going backwards. So we're going to do an inverse normal distribution. So we're going to come over here to our calculator, turn it on, and we want, here in blue it says distribution, and that's what we want. So we're going to hit the blue key, distribution, and look right here, inverse normal. That's exactly what we want. So we're going to go ahead and go to 3. The area, well, that's this area here, that's 0.1. And then remember, this is a standard normal distribution because we're using z-scores. So that means that the mean will be 0 and the standard deviation will be 1, because that's always the case for a standard normal distribution. Now we're going to hit paste and enter. We get our z-score. It's negative, or not our z-score, but our critical value. It's negative 1.28. Okay, now let's go ahead and find it using the chart. So on the chart, we're going to just look up this area and find the z-score. Pretty much just how we did it with the calculator. We're just going old school. So we know that we need an area of 0.1. So we're going to go to the standard normal charts. And remember, in the middle here, these are areas. And we're going to use the area to find the z-score by looking it up backwards. I see it's a really common mistake. People looking up z-scores and then trying to find like an area and using that's going to get you really messed up. Definitely don't do that. You want to understand the z-scores in the areas. So, okay, we have an area of 0.1. So in this big sea of numbers, we need to find 0.1. So coming in here, let's look at this. Let's look at these things. So here's a 0.0, so that's too big. So we'll keep coming down. And here's 0.09. And here we have 0.1. So it seems like we should go this way more. Here we've got oh, look at this one. 0.10027. So that is extremely close to just 0.1. So this is the value we want to look up backwards. Oh, and I'm blocking it using the calculator. My apologies. Now look at how close this number is to 1. Extremely close. So we're going to work backwards. And we see it corresponds to negative 1.2 and 0.08. So negative 1.28 would be the z-score that corresponds with that. So on our chart, we would again arrive at the same value. So there's a quick way to check your answer too. Really easy way. That takes hardly any time at all. And that's our critical value. So now we need to find our test stat or our p-value and see if we land in this region. So to do that, we need to identify the test. Well, we already know we're using a z-test as we see above. So the z-test uses the following formula, right? We have a sample average and we have a population average. And so the only formula that uses both of those is x bar minus mu over sigma divided by the square root of n. That'll give us our test stat, our z-score that will correspond to our test statistic. So if we just plug all these things in, we'll do it using the calculator here after we do it using the formula. That's going to be 4.2 minus 5.1, right? The two means subtracted, divided by 1.8 over the square root of n, which our n was 38. Let's go ahead and punch this in the calculator. So first we need to type a fraction. So we see here in green that F1, the function 1 menu, that actually has fractions in it. So hit the green key and then that, because that's green. So you hit the green key to get to the green thing. And we see we have a fraction as our first option. So we choose that. The top numbers are just going to be 4.2 minus 5.1. We're going to come down and wants another fraction. So we type green key F1. And we choose the first one for our fraction. We do 1.8 over square root is what we need. And so we are going to use this blue square root key. So we hit the blue key and then square root and then 38. We hit enter. And we get this as our z-score, negative 3.08. So this is pretty handy as our z-score. That's going to, if we were to graph this, right? Well, if this is negative 1.28, minus 3.08 is way over here. So we are definitely in the shaded region, which we kind of expected based on what we talked about before. And so we would say, oh, well, we reject the null hypothesis. And we would go on to make our conclusion and state it. But let's go ahead. Let's also find this using the calculator method. So in the calculator method, if you don't want to use the formula, or maybe you want to check your work really quick, it's really simple. We're doing a z-test. So we're going to go to stats because this is a statistical test. So we're going to go to stat and then we're going to go to tests. And in here, our very first one is a z-test. So we're going to choose that. Now we don't have data. We were given the statistics directly. So we're going to go to stats. And in here, we've got our mu naught. Well, we said that that is 5.1. And then our sigma, well, that's 1.8. See, it's just asking for everything that we already have. X bar, that's just 4.2. It's basically just going to do this formula for us using these things. Then we have 38 for n. And for our mu, so we said that mu is less than 5.1. And we said that mu naught is 5.1 right here. So we want to be less than that. So we're going to be less than mu naught. So we're going to be this one right here, less than that. And you can go to calculate, but I actually think draw is pretty insightful. With this small of a z-score though, It's you're not going to see hardly anything on it. Watch. So we're going to hit draw. And it's going to tell us our p-value. It's 0.001. So an incredibly small p-value. So p is equal to 0.001. Normally you would shade this. But that is so small. So little of this curve has been shaded. It's actually it's this right here. You can't even tell that it's been shaded. That's how small this is. So that's our p-value, and our z-score, we see we get the exact same z-score. Now remember, our alpha was 0.1. Well, so let's write that down. Alpha is equal to 0.1. Well, our p-value is way less than alpha. Essentially, what the p-value is it's the area that would be shaded due to our test statistic. So it would be like this in red, all this like little itsy bitsy area in red here. And if we were to look this up using the chart, we would just look up the z-score and see what area it covers. So that'd be 3.08. So we go to our standard normal. Here's negative 3.8. Oh no, it's 3.08. So it'd be 3.0 and then 8. And if we were to draw across here, that would be the value, 0.00104. So we get the same p-value. This one has a couple more digits. But we see we get 0.001 again using the table. So there's a way you can check that. And based on this, we land in the shaded region. Every way we do it, we're going to get the same thing. We are going to land in the shaded region. So we say we're so far away from what it originally was that we'd say we reject the null hypothesis, H naught. Because this is essentially H naught. The middle is H naught. And we're so far away from it based on the study that we did that we were like, oh yeah, this doesn't seem right. This seems like this seems too big. The values we got are much smaller. So we don't think that's right. And so our study has produced evidence. Here we have a pretty compelling argument that the population mean isn't 5.1. We think it's actually less than that. So that would be our conclusion. And since our claim was that it's less than that, well, we have evidence to support that. Now, we can't say that this is true. There is evidence that this is true. Well, we could technically say that, but we can't say that this is just straight up true because we only did one study. One study only reveals so much. If we did a bunch of studies, our argument would get more and more compelling as we went. So we would say there is evidence, because that's what we did. We produced evidence. There is evidence to support the claim. To support the claim. Now, this evidence that we've produced here, some teachers aren't happy with this wording because it's pretty vague. What is the claim exactly? So some teachers want you to write that out. So we would instead write, if you have a teacher that wants like more detail, you would write, there is evidence to support the claim that, and the claim was that the average American spends less than 5.1 hours a day watching television. You would literally just write this right after it, and that would be what you write. In fact, most of the time, the last sentence is going to have what you're going to write. Every now and then, they stick it somewhere else in the problem, but a lot of problems have it at the very end. So if you want to be extra detailed and demonstrate that you know what you're talking about when you say that you're supporting the claim, so we're supporting the idea that it's actually lower than 5.1. Americans spend less time watching TV on average than what's claimed here. Now, if we were to also do this with the p-value method, you'd also want to include the statement that p is less than alpha. And right, p was 0.001, and that's less than 0.1. And because of that, you would reject H naught, and you would say that, oh, then obviously we support this claim. Now, a trick I like to do with students, because sometimes they just have a hard time with this, they can get the reject H naught, but they have a hard time with the claim. Well, think about this. If we reject H naught, that means we think H naught is not true, right? We rejected it. So I would write false, because we don't think it's true. So if we think this is false, well, then this other one has to be true, because it's the only other option that we gave ourselves, and it's the opposite. In this case, it's less than. It's different than H naught. So we think this is true, and so we'd say, oh, well, there's evidence to support this. And that's how to simplify things if you're having a hard time seeing how it all sort of comes together. And that's how you do this question. If you have any questions about this, definitely feel free to drop a comment below. If you're a Citrus College student, definitely drop by online tutoring. We are there to help you succeed. And subscribe, and we'll catch you in the next problem.